This is a graphical user interface that implements the algorithms that I have proposed in my PhD dissertation, as well as some other standard algorithms. Here I want to synthesize a non-Gaussian signal starting from a non-Gaussian reference signal, and I will have to click on this Halt button here that will open up another GUI which will guide us through our synthesis procedure. There are some parameters that can be input here. I will just mention a few of them. We have B here, which is the SN curve slope. In our experimental campaign, we estimated this parameter to be approximately equal to 9 for our aluminum samples. And I also have to mention this zeta parameter, which represents the damping ratio of our device under test. It was about 1%. So I will set 1% there. And then I will also mention this delta F, which is the resolution in frequency, and I will set a value 0.1 here. Then I can run the GUI, so we click on this run button here, and I have to insert a reference signal. So I will go to the right folder, I will choose a signal that can be either a MATLAB file, or it can be an Excel file, or also a text file. I will input a MATLAB file, and the MATLAB file can be of different types. For example, it can be a structure which contains just one vector, which represents the time series of the signal, and it should also contain a scalar representing the sampling frequency, for example. Or you can input another type of MATLAB file. For example, you can input another file which contains a vector which represents the time series, and then of course there will appear a dialog box during the run of the program that will ask you to input the sampling frequency yourself. So there are different possibilities. Here I will just input this file here, which contains both the signal and the sampling frequency. And you can see a dialog box here which asks me if I want to extract some parts of the signal that I have input, but I will say no. And there is another one that asks you if you want to do a preliminary analysis of the signal. Here I can click yes, and you can plot both the PSD and the signal itself. So you can take a look at the signal, you can take a look at the spectrum, and you can see that the Nyquist frequency is 65 Hz, so the signal was sampled at 130 Hz. Based upon these plots here, you can choose to filter the signal, for example, but I will say no. You can also modify the frequency resolution, which was this 0.1 Hz, and I will say no here. You can also change the duration of the signal that will be synthesized. And in this case, I will do it. So here you can see that there is a duration of 600 seconds. This has nothing to do with the duration of the signal. The duration of the signal was about 1105 seconds. So I can set that kind of duration here. I will not synthesize a signal aimed at accelerated tests. I will just synthesize a signal that is aimed at preserving both the kurtosis and the FDS of the signal with the same duration as the reference signal. So here I will click yes, and then I will set 1105. And then here you have to choose one of the algorithms that are proposed in the PhD dissertation. I will choose the first one, which preserves both the FDS and the kurtosis value. I have to input the lower frequency from which the FDS will be computed, and also the upper frequency. This is like the spectrum for the FDS. I can start at about 2 Hz and go all the way up to 50 Hz. This is the last parameter that you have to input before the synthesis procedure actually starts. You have to insert the expected life under the inserted load. In our experimental campaign, this value was about 1.66 hours. And click OK, and then here the FDS will be computed, and at the end of the calculation this dialog box asks me if I want to load another file or another situation, but I will say no. And the synthesis procedure has already occurred here, because here when I click OK, the calculation of the FDS of the synthesized signal will start, but the signal has already been obtained. So I will click OK, the FDS is calculated here, and here we see the results. This is the statistical parameters box. In the first row, you can see that the kurtosis values are pretty close. This is the reference signal kurtosis, this is a synthesized signal kurtosis. And here you can see the FDS. You can see that the two curves are very close to each other. And here you can see the PSD. The PSD curves are different because we are not using the PSD as specification. Now let's take a look at the signal. This is the synthesized signal. And I can also save it. I will do it later. But you can also compare it with the reference signal. You can see that the two signals are quite different, because this is the reference signal and it looks much smaller than this synthesized signal here. But they have the same FDS, and also more or less the same kurtosis engineering wise. So sometimes it can be even closer than this, so it depends on the different runs of the algorithms. This difference here depends mainly on the non-stationarity of this reference signal here, and also on the characteristics of the algorithm that was used in the synthesis procedure, but I will not delve into these details. So here I have the signal, and I want to save it. Let me do it like this. I will click again on this plot synthesize signal here. This plot will open up again, but I will still have this dialog box which asks me if I want to save the signal, and in this case I will click yes. I will choose a folder and also a name, which I can leave it like this. Xsynth will be the name of the file containing this signal. And I can choose a text file, a MATLAB file, or an Excel file. And I will choose a MATLAB file. That's pretty much it. I just wanted to illustrate how a non-Gaussian signal can be synthesized using the GUI that I developed during my PhD program.